simple interest for 3 years is 60 plus 60 plus 60, 180. Compound is 191.01. So the compound interest is always more than the simple interest. Okay, this you should keep in your mind. The compound interest is always, even for the 2 years,
Let us wait for 2 minutes, okay?
even for 2 years, the total simple interest is 60 plus 60, 120. Whereas the compound interest 60 plus 63.6, 123.6. So the compound interest is always more than the simple interest. This you should keep in your mind because this will be useful for many other calculations. Okay. So thank you so much. We'll close at this today. We will meet in the next Thursday. Okay. Okay. There is a formula for compound interest that we will take it up in the next class because I am actually helping. I mean, trying to solve the question without formula. But formula is there. It is there in your book. We will use that at a later point of time. Okay. All the best. Thank you, Pa. Thank you. Thank you. Thank you, children. Thank you.
Okay. Good evening, everyone. So today we'll be discussing questions from periodic classification of elements. But before getting into the questions and all, let us have a quick revision of the chapter. Fine. Okay. So this periodic classification of elements will be your third chapter in 11th standard, right? So in this chapter, you would have studied about a periodic table and different periodic properties and the way in which elements are present and all that, right? What are all the periodic properties you studied in this chapter? What are all the periodic properties you studied?
Ma'am, it includes electronegativity, electron affinity, nuclear charge,
Yeah.
ionic radii, and I don't sure about the fifth one, ma'am.
Okay, fine. Effective nuclear charge. You told me nuclear charge, but we would have studied effective nuclear charge also. Okay,
Okay.
very good, Pratika. Fine. So, in periodic classification of elements, you would have studied what is periodic table and the way in which elements are present, and you would have studied about groups, periods, different blocks of the periodic table, and you would have studied about the IUPAC nomenclature of the elements whose atomic number is above 100, and periodic properties like effective nuclear charge, atomic radii, ionization energy, electron affinity, electronegativity, and also acidic and basic properties of metal oxides and non-metal oxides, right? Actually, this is a very simple topic and also very important topic too, because this is one of the important topics in inorganic chemistry. So let us start the chapter. Um, this is basically a periodic table, right, in which elements are present. These elements are arranged based on its atomic number, right? What is atomic number? What is atomic number?
It is number of proton or number of electron present in an atom, ma'am.
Yes. So basically, in this periodic table, elements are arranged based on the atomic number. That's it. And also, we have lot of rows and columns. Basically, these rows are called as periods and columns are called as groups. How many periods and how many groups are there in periodic table? Horizontal rows are called periods and vertical columns are called groups. So there are 7 periods and 18 groups are present in periodic table. Generally, period number represents the valency shells number and group number represents the number of valency electrons, right? Let us have an example. Let us take lithium. What is the period number of lithium? In which period lithium is present? In which period lithium is present? Lithium is, yes, yes, yes. Yeah, someone told me, right? In which period lithium is present?
It is in second period,
It
ma'am.
is in second period. Very good. Okay. See, this is the periodic table. Lithium is present in second period, right? Let us write the electronic configuration of lithium. Lithium's atomic number is 3. Its electronic configuration is 1s2, 2s1. So the last electron is present in second shell. So second shell is the valency shell. So basically, period number represents the valency shell's number. So in second period, we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And for all these elements, valency shell's number will be 2. Okay. For example, let us take scandium. Scandium is in fourth period, right? Then what will be its valency shell? 4. As simple as that. Is that clear? And similarly, group number represents the number of valency electron. Let us take this first group. In first group, we have hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. And for all these elements, number of valency electrons will be just 1. Okay. For example, lithium, how many valence electrons are there in lithium? Just 1. So group number is 1 and number of valence electron is also 1. And for group 2, valence electrons will be 2. Let us take calcium. What is the atomic number of calcium? It is 20. So the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So the last electron is present 4s. And how many electrons are there in valency shell? 2 electrons, right? So group number always represents the number of valency electron and period number always represents the valency shell. Okay, so this is for first and second group. For 13th group, for 13th group element, the number of valency electrons will be 3. So group number is 13 and what is the number which is present in one's place? It is 3. So all the 13th group elements will have 3 valence electrons. Similarly, 14th group elements will have 4 valence electrons. So how many valence electrons will be present in phosphorus? Where is phosphorus? It is here. Now tell me how many valence electrons will be present in phosphorus?
5.
Very good, it is 5 because phosphorus is in 15th group, right? So number of valence electrons will be 5. Okay. So just from the group number and period number, we can tell about its valency shell and number of valency electrons also. And also this periodic table is classified into 4 blocks: S block, P block, D block and F block. This classification is based on subshell into which the last electron is getting entered. For example, let us take aluminium. What is the atomic number of aluminium? Aluminium's atomic number is 13, right? So the electronic configuration is 1s2, 2s2, 2p6, 3s2 and 3p1. So which is my last electron? This electron. And this electron is getting entered into p subshell. So aluminium will come under p block element. Let us take calcium. Calcium's last electron is this one and this last electron is getting entered into S subshell. So calcium will come under S block element. Let us take scandium. Scandium's atomic number is 21 and its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d1. Now tell me, scandium will come under which block element?
D block element.
D block element, as simple as that. Okay. Now we understood what is the physical significance of period number, group number, and how this periodic table is classified into 4 blocks. Now let us understand how to write the IUPAC nomenclature of elements whose atomic number is greater than 100. For that, you would have studied rules. I mean, there is no rules for that, but for every number, we'll be having a root name, right? For example, for 0, the root name is nil. For 1, the root name is un. For 2, the root name is by. For 3, what is the root name? tri. And for 4, what is the root name? It is very easy. You must have learned, right? For what is the for 4, what is the root name? It is quad. For 5, it is pent. For 6, it is hex. For 7, it is sept. For 8, oct. And for 9, it is een. And for every root name, there is a abbreviation. So for nil, it is n. For un, it is u. And for bi, it is b. Small u, small b. And for tri, it is t. It is q for quad, p for pent, hex for h for hex, s for sept, o for oct, and e for een. That's it. Let us take an example. For example, let us take the element whose atomic number is 100, and we have to write the IUPAC nomenclature of this atomic number. So this is 1. For 1, what is the root name? It is un, un. And what is for 0? It is nil. And again there is 0, again it is nil. And all the name should have the suffix of IUM. So IUM. So this is the IUPAC nomenclature of this number 100. Okay. And what is the symbol of 100? You have to write the abbreviation of each root word. That's it. So for 1, it is U. And for 0, it is nil. So it is N. And again N. So this is the symbol of atomic number 100. That's it. Is that clear? Let us write for 107 then. So for 1, it is un. And for 0, it is nil. And for 7, it is sept. And you have to write the suffix as IUM. And what is the symbol? UNS. That's it. Is that clear? Is that clear? Okay. Fine. So now we'll move on to some periodic properties, okay, which are very, very important in this chapter. So the periodic properties, what we studied in this chapter is effective nuclear charge, radius, ionization energy, electron affinity, electronegativity. These are all the 5 very, very important periodic properties, okay? And we have to know what are those and what are their periodic trends in the table, okay? So as we move from left to right, what happens to effective nuclear charge? And as we move down the group, that is top to bottom in the group, we have to know what is happening to effective nuclear charge and all that, okay? So let us have a quick recap, okay? First is effective nuclear charge. Definitely, this is different from your normal nuclear charge, right? So what is the basic difference between nuclear charge and effective nuclear charge? Nuclear charge and effective nuclear charge. They are 2 different terms. Nuclear charge is nothing but it is the charge of the nucleus. How nucleus will get its charge? From the proton, right? Because in every nucleus there will be proton and neutron, but there is no charge for the neutron. Only we have charge for proton, which is positive charge, right? So the charge of the nucleus is only due to the presence of proton. So let us take example of hydrogen. Atomic number of hydrogen is 1. So what is the proton count? It is 1. So what is the charge of the nucleus then? Plus 1. That's it, right? Because hydrogen got only 1 proton whose charge is plus 1. So the nucleus charge also plus 1. How about helium? What will be the proton count of helium? It is 2. So what will be the nuclear charge of helium then?
Plus 2.
Very good. It is plus 2. So for lithium, atomic number is 3, proton count is 3, so nuclear charge is also plus 3, right? So what we can observe is nuclear charge is nothing but the atomic number, right? So nuclear charge can be represented with an alphabet Z, same as atomic number. But effective nuclear charge is little different. Effective nuclear charge is nothing but the original nuclear charge experienced by the valency electron of the atom. Let us take example of lithium. Atomic number of lithium is 3. So this is the nucleus which contains 3 protons, and also there will be electron, but I'm writing only protons here. So around this nucleus we'll be having electrons, right? So what is the configuration of lithium? It is 1s2 and 2s1. So in first shell we'll be having 2 electrons, and second shell we'll be having only 1 electron, right? So all these 3 electrons will experience a attractive force from the nucleus, but first electron will the electron which is present in first shell will experience more effective more nuclear charge than the electron which is present in second shell. What is the reason? What is the reason for this difference? The electron which is present in second shell will experience a very little nuclear charge than the electron which is present in the first shell. And what is the reason behind that?
Because the first orbital is near to the nucleus, ma'am.
Okay. So Tatvatika is telling me that this is due to the distance. So second shell is far from the nucleus, and first shell is nearer to the nucleus. So obviously first shell's electron will experience a quite higher nuclear charge than the second one. Not only that is the reason, there is another very important reason is between this nucleus and the valency shell, or between this nucleus and the second shell, there is a inner shell, right? In this inner shell we have 2 electrons, and these 2 electrons are revolving around the nucleus, right? So these 2 electrons will shield the nucleus. Now this second electron cannot experience all the nuclear charge of this particular nucleus. Why? Because this inner electron will shield the nucleus, right? So only a particular quantity of nuclear charge will be experienced by this second electron. So that is called effective nuclear charge. So original nuclear charge will be more, but all the nuclear charge will not be experienced by the valency electron. Why? Because there are inner electrons. These inner electrons will shield the nucleus, right? Is that clear?
Yes, ma'am.
So there is a formula to calculate this effective nuclear charge. Let us see the formula alone. Effective nuclear charge is nothing but original nuclear charge minus the quantity of nuclear charge which was shielded. Okay. So this is the formula to calculate effective nuclear charge. This S is called screening constant or shielding constant. Fine. That's it. So now we understood the difference between nuclear charge and effective nuclear charge, and we have to represent this effective nuclear charge by Z star. Now we'll understand the periodic trend of effective nuclear charge. So as we move from left to right in the periodic table, which means we are moving from, let us say we are moving from lithium to neon. So we are moving from left to right in a periodic table. What will happen to the effective nuclear charge? Will it get increased or decreased?
Decrease.
Okay, Vashni is telling that as we move from left to right in a periodic table, effective nuclear charge will get decreased. Is there any other answer? As we move from left to right in the periodic table, effective nuclear charge increases. Let us see the reason behind that. Let us take the elements which are present in second period. Okay, let us take lithium, beryllium, boron. Okay, what is the atomic number of lithium? It is 3. Atomic number of beryllium is 4. Here it is 5. So what is the electronic configuration? I don't write the electronic configuration. Let us write the proton count and electron count alone. Okay, what is the proton count of lithium? It is 3. What is the electron count of lithium? It is also 3. As far as beryllium is concerned, proton is 4 and electron is 4. As far as boron is concerned, proton is 5 and electron is also 5. As we move from left to right in a periodic table, proton count is increasing, and at the same time electrons count is also increasing, right? By increasing the number of protons, we can understand that nucleus is getting more number of protons. So definitely charge will get increased as we move from left to right in a periodic table. And this electron will not influence the positive charge at all, because these electrons are getting added to the same shell. What is the electronic configuration of lithium? 1s2, 2s1. Beryllium 1s2, 2s2. This is 1s2, 2s2, 2p1. So as we move from lithium to beryllium, proton count is increasing, electrons count is also increasing, but there will not be any impact at all, because the electrons which are getting added are entering into the same shell. In lithium, the electron was in second shell. Now in beryllium, the new electron is also getting entered into the second shell itself. So there is no biggest impact on the nuclear charge here. So as far as electrons are concerned. So as we move from left to right in the periodic table, protons counts are getting increased, due to which effective nuclear charge is getting increased. So as we move from left to right in a periodic table, effective nuclear charge increases. Okay. As we move down the group, as we move from top to bottom in a periodic table, what will happen to the effective nuclear charge? As we move down the group, effective nuclear charge will get
Decreases, ma'am.
very good, decreases. How? Let us take an example of lithium and sodium. The electronic configuration of lithium is 1s2, 2s1, and for sodium, the electronic configuration is 1s2, 2s2, 2p6, and 3s1. So in lithium, the valency shell is second shell. In sodium, the valency shell is third shell, right? So here, inner electrons are just 2. Here in sodium, the inner electrons are 10 electrons. As we move down the group, number of inner electrons are getting increased. So shielding is getting increased. So due to which last electron will experience lesser nuclear charge. So as we move down the group, effective nuclear charge is getting decreased. That's it. So if we understand this effective nuclear charge very clearly, then rest of the properties were very simple. How about radius? Basically, what is radius? It is the distance between the center of the nucleus to the valency shell of the atom, right? So if the effective nuclear charge increases, what will happen to the radius of the atom? If effective nuclear charge increases, then what happened to the radius of the atom? If effective nuclear charge increases, that is, if the electrons which are present in the valency shell is experiencing a more nuclear charge from the nucleus or more attractive force from the nucleus, what will happen? This electron or this orbit or this shell will move towards the nucleus, right? Which means the atom is, what is happening to the size of the atom?
It decreases, ma'am.
Yes, the radius will get decreased, because this nucleus is attracting the valence electron very powerfully, so that the radius or the distance between the nucleus and the valency shell will get decreased, so size will get decreased. So effective nuclear charge increases, then radius of the atom decreases. So they are inversely proportional. So as we move from left to right in a periodic table, effective nuclear charge increases, so size of the atom decreases. So how about in group top to bottom? Effective nuclear charge is getting decreased, so radius will get increased. That's it. Next is in this radius, you would have studied about covalent radius, van der Waals radius, metallic radius, and all that. And you would have studied about the radius of isoelectronic species also. So we'll be discussing questions related to all those radius and all. Fine. Next, we'll move on to ionization energy. What is ionization energy? What is ionization energy? Minimum amount of energy to remove the loosely bound electron from an isolated gaseous atom, right? For example, let us take lithium. Okay, atomic number is 3, and its electronic configuration is 1s2, 2s1. So in lithium, inside the nucleus we'll be having 3 protons, and in first shell we'll be having 2 electrons, and in second shell also we'll be having, in second shell we'll be having only 1 electron, right? Okay. So this valency electrons are considered to be loosely bound electron, because valency electron will experience very less nuclear charge, right, due to the shielding effect. So this valency electrons are considered to be loosely bound electron. To remove this electron, we have to supply a particular amount of energy on this electron, no? So the minimum amount of energy to knock out this valency electron is called ionization energy. Okay, basically we are supplying the energy on this electron. Whenever you are supplying the energy on any system, then you have to represent that energy with positive sign. So always ionization energy will be positive, because this is the amount of energy we are supplying on the electron to remove that. Okay, and unit of ionization energy will be in terms of, it can be in terms of kilojoule per mole, kilocalories per mole, and all that. Fine. Now tell me, as we move from left to right in a periodic table, ionization energy will get increased or decreased?
Increase.
Very good, it will get increased, because as we move from left to right in a periodic table, effective nuclear charge is getting increased. So valency electron will experience more attraction from the nucleus. Now this, as we move from left to right in a periodic table, valency electrons are very tightly bounded towards the nucleus. Now removing this electrons will be very difficult, so we have to supply more amount of energy. So effective nuclear charge increases, then ionization energy also increases. They are directly proportional. So as we move from left to right in a periodic table, ionization energy increases, and as we move down the group, ionization energy decreases. Fine. So here we are talking about the ionization energy, right? So ionization energy is directly proportional to effective nuclear charge. And how this ionization energy is related to the size of the atom? How ionization energy is related to size of the atom? Is it directly proportional or inversely proportional?
It is inversely proportional.
Very good. It is inversely proportional. So as the size decreases, effective nuclear charge is getting increased. So ionization energy will also get increased. So ionization energy is inversely proportional to size of the atom. Okay. So ionization energy will not only depend on this effective nuclear charge and size. There are few other factors which influence this ionization energy. There are two, 3 points. We'll see that now. So this is first point. This is second point. This is third point. Let us take a configuration of oxygen and nitrogen. Generally, in periodic table, nitrogen is nitrogen is in the rightmost corner, right? Oxygen, nitrogen, oxygen. Atomic number is 7 and the atomic number is 8, right? So based on the normal trend, among nitrogen and oxygen, we'll think oxygen will have higher ionization energy, because as we move left to right in the periodic table, ionization energy increases. So what we'll be expecting is oxygen will have more ionization energy than nitrogen. This is what is our expectation. But this is not the case actually. Why? Because the electronic configuration of nitrogen is 1s2, 2s2, 2p3. And the electronic configuration of oxygen is 1s2, 2s2, 2p4. Effective nuclear charge may greater for oxygen, but the configuration here is just 2s2 and 2p4. But the configuration of nitrogen is 2s2 and 2p3. What is 2p3 configuration? It is half-filled configuration, right? As far as oxygen is concerned, it is 2p4. It is just partially filled configuration. There is a hell lot of difference between partially filled configuration and half-filled configuration, right? Half-filled configuration and completely filled configurations are more stable than partially filled configuration. Am I right? Half-filled and completely filled configurations are more stable because of more exchange energy, right? So if you compare the stability of nitrogen and oxygen, nitrogens are more stable than oxygen. So we cannot remove electron from the most stable configuration. So the effective nuclear charge of, though the effective nuclear charge of oxygen is greater than nitrogen, still we have to supply more amount of energy on nitrogen to remove this electron because it is in the stable configuration, right? So the third factor is its electronic configuration. If the electronic configuration is half filled or completely filled configuration, then to remove electron from that kind of configuration is very difficult. So for half filled and completely filled configuration, ionization energy will be more irrespective of the trend. Is that clear? That is third point. Fourth point is, let us take two scenarios, okay? In first scenario, the electron is present in second shell, okay? In another scenario, the valence electron I'm talking about is present in third shell. In which scenario we can remove the electron easily? In first case, the electron is present in second shell, or the valence electron is second shell. In second scenario, or in second case, the valence electron is present in third shell. So in which case we can remove the electron easily?
From the third shell, ma'am?
Yes, because third shell is very far from the nucleus. So we can remove the electron which is present in the third shell. Similarly, now I'm going to take two cases. In first case, the electron is present in S subshell. And in second case, the electron is present in P subshell. In which case we can remove the electron easily? In which case we can remove the electron easily? From P subshell, right? So why? Because this S subshell is very much near to the nucleus, right? So this is called penetration effect. So if the electron is present in the S subshell, it is very difficult to remove. So we have to supply more amount of energy on this S electron. But relatively, P electrons can be removed easily. Relatively, d electrons can be removed easily. Relatively, f electrons can be removed easily. So for s electron, ionization energy will be more, and for f electrons, ionization energy will be less. So this is the order. Okay, so ionization energy depends on this penetration effect also. Okay, is that clear? And finally, there's another point or another factor, number of inner electrons. Now tell me, if number of inner electrons are more, then is it easy to remove the electron? I mean, is it easy to remove the valence electron or not? If there are more number of inner electrons.
Yes, ma'am.
Yes, because if the inner electrons are more, then shielding will be more. So nucleus are perfectly shielded now. So nucleus will cannot show attraction on the valence electron. So it can be removed easily. So if inner electrons are more, then ionization energy will be less. So these are all the other factors which influences the ionization energy, right? So whenever you are checking for the ionization energy, not only you should see effective nuclear charge and size, definitely you have to check for the electronic configuration, penetration effect and all that. Is that clear? And also you have to have a good knowledge of successive ionization energies. Successive ionization energies is if you remove the first electron from one atom, that is called first ionization energy. From the same atom, you are removing second electron, then that is called second ionization energy. So you may get questions from successive ionization energies also. That's it. Now the third point is okay. Before getting into another periodic property, in periodic table, which element will have the highest ionization energy? In periodic table itself, which element will have highest ionization energy? As we move from left to right in the periodic table, ionization energy increases, which means the element which is present in the rightmost corner will have highest ionization energy, right? Which can be your 18th group, right? In 18th group, as we move from top to bottom, ionization energy decreases. So which element will have highest ionization energy? In 18th group, which is the topmost element? Helium.
Helium.
Helium, that's it. So helium got the highest ionization energy in the periodic table. Fine. And also helium is inert gas. Inert gas, so removing electron from helium is not easy at all. That's it. So next we'll move on to electron affinity. So electron affinity is nothing but it is the attraction towards electron. Now tell me how effective nuclear charge and electron affinity will get related. How effective nuclear charge and electron affinity will get related. Electron affinity is nothing but affinity is called attraction, right? So attraction towards electron. If the nucleus is so much powerful, if the effective nuclear charge is so much high, then how about its electron affinity? If the nucleus is so strong, yes, Varshini?
High.
Yes, definitely. If the nucleus is very strong, if the nucleus is very powerful, then this nucleus can easily add one more electron, right? So effective nuclear charge is directly proportional to electron affinity. So now let us come to the trend here. Effective nuclear charge is directly proportional to electron affinity. So as we move from left to right in a periodic table, electron affinity increases because effective nuclear charge is getting increased. As we move down the group, effective nuclear charge is getting decreased. So our electron affinity is also getting decreased. Fine. So in many places, effective nuclear, in many places, electron affinity term will be replaced with a term called electron gain enthalpy. What is electron gain enthalpy? See, let us take an atom A, which is in a gaseous state. Okay. Now, this atom got superb effective nuclear charge. So, this can add one electron, right? So, this atom will get converted into anion. So, this atom got good attraction towards electron. So, this atom was converted into anion. So, electron affinity is good. Now, this atom, after gaining one electron, will release a particular amount of energy. That particular amount of energy is called electron gain enthalpy. If an isolated gaseous atom, after attracting one electron or after gaining one electron, it will release a particular amount of energy called electron gain enthalpy. Okay, if electron affinity is more, then atom will release more amount of energy. So electron affinity is more, electron gain enthalpy will also be more. But the point is electron gain enthalpy is the amount of energy which is getting released. So what should be the sign of this energy? What should be the sign of this electron gain enthalpy?
Minus, ma'am.
Very good, it is minus. Okay, but it is not the case in ionization energy. Ionization energy will always be positive. Electron gain enthalpy will be negative. Okay, so here one neutral atom is gaining one electron. This atom now got converted into anion. Here a particular amount of energy was released. Here this is first electron affinity, and here the particular amount of energy was released, which I'm representing it as electron gain enthalpy. I'm going to write a hypothetical number here, maybe minus 200 kilojoule. This is a hypothetical number. Okay. Now, to this anion, I'm going to add one more electron. Now, tell me, is it really easy to add one more electron to anion? Was it easy?
No, ma'am.
No, it is very difficult because here proton count, let us take proton count is 12. Electron count also will be 12. So adding one more electron will not be a problem. But now this is anion where electrons count is more. It is already a negatively charged species. So to which we cannot add another negatively charged species because of repulsion. So definitely second electron affinity will be lesser than the first one, right? So first electron affinity will be greater than the second electron affinity. Okay, here sometimes energy may release in some cases, but definitely the energy released will be lesser than the first case. Okay, electron gain enthalpy may be minus 80. Okay, because here electron affinity is less. Okay, now to this anion I'm adding one more electron, which is very very difficult. So here third electron affinity will be very much less. Here in this case we cannot add third electron itself. So in this case we may have to supply energy to add this electron to this anion. So third electron gain enthalpy may be positive because we are supplying the energy and we are adding electron to that. So in most of the cases first electron gain enthalpy will be negative because adding one electron to neutral atom will not be a problem, but adding second electron, third electron will be definitely difficult. So another successive electron gain enthalpies will be less negative or sometimes positive also. Is that clear? Is that clear?
Yes, ma'am.
Okay. And there are factors which will influence as electron gain enthalpy or electron affinity. So the first factor is definitely effective nuclear charge. Effective nuclear charge increases, electron affinity also increases. Size increases, effective nuclear. If size increases, electron affinity will get
Decreases, ma'am.
very good decreases. So effective nuclear charge and size and electron affinity are inversely proportional. Next, half-filled and completely filled configuration will have higher electron affinity or lesser electron affinity. Half-filled and completely filled configuration.
Higher one.
Okay, Vashni's answer is higher. How about Tatvatika?
Ma'am, I think it will be lesser because it is all labeled.
Fine. So half-filled and completely filled configuration is very stable configuration. This atom need not add any other electron to get stabilized, right? So half-filled and completely filled configuration is already stable. So this atom will not gain one more electron at all. So electron affinity of half-filled and completely filled configuration is nearly zero. Nearly zero. So electron affinity of half-filled and completely filled configuration is nearly zero. Okay. For example, I have a half-filled configuration atom. Okay, to which I have to add one electron. Definitely, it will not gain electron very easily. So we have to supply energy and we have to add electron. So to in that cases, for half-filled and completely filled configuration, electron affinity is zero and electron gain enthalpy will be positive because we are supplying the energy and we are adding electron. Is that clear? Electron affinity is zero, so electron gain enthalpy is positive. It is definitely not negative. Is that clear?
Yes, ma'am.
That's it. Okay. This is all about electron affinity. Next, we'll move on to electronegativity. Electronegativity is very, very simple. Generally, electronegativity will be represented with a term chi. Okay. Fine. What is electronegativity? For example, I have atom A and another atom B, and these two atoms are sharing these two electrons to form a covalent bond. But in among A and B, if the effective nuclear charge of B is greater than A, then this B atom will attract the shared pair of electrons towards itself. Because what is covalent bond? Covalent bond is a bond which is formed by the mutual sharing of electrons. So these two electrons are common for both the atoms. So electron has to be at the center, right? But the effective since the effective nuclear charge of B is greater than A, what this B is doing? It is attracting the electron towards itself. So capacity of an atom to attract the shared pair of electrons towards itself is called electronegativity. Is that clear? So due to this electronegativity property, this atom will gain a partial negative charge and this atom will gain partial positive charge. See, atoms will not gain complete positive and negative charge. Why? Because this atom will attract the electron to some extent. Atom cannot take the electron completely. It will attract to some extent. That's it. So atom B will gain partial negative charge and atom A will gain partial positive charge. Definitely it is not complete positive and complete negative. Atom B cannot take this A's electron completely. Okay, fine. But definitely 2 electrons are not at the center, it is towards B. Okay, that is electronegativity. Now tell me how effective nuclear charge and electronegativity is getting related. Effective nuclear charge and electronegativity are they directly proportional or inversely proportional? Effective nuclear charge is nothing but which directly implies the strength of the nucleus, right? If the effective nuclear charge is more, then the capacity of attracting the electron will also be more, right? So effective nuclear charge increases, electronegativity also increases. So they are directly proportional. So as we move from left to right in a periodic table, if, electronegativity
Increases, ma'am.
and from as we move down the group, electronegativity decreases. Now there is a famous question. In periodic table, which element got highest electronegativity? Which element will have highest electronegativity in periodic table?
Fluorine, ma'am.
Very good, it is fluorine. Because as we move from left to right in the periodic table, electronegativity increases. So what is the rightmost group? 18th group. But what is electronegativity? Capacity of an atom to attract the shared pair of electrons. What is shared pair of electrons? Electron which is present in the chemical bond. But 18th group element cannot form bond at all, right? So we should not consider this 18th group. Now we have to check for the 17th group element. So what are all the elements which are present in 17th group? Fluorine, chlorine, bromine, iodine, astatine. So as we move down the group, effective nuclear charge decreases, electronegativity also decreases. So logically, fluorine will have the highest electronegativity. Okay. Okay. Now we'll come to electron affinity. In periodic table itself, which element will have highest electron affinity? Which element will have highest electron affinity?
Chlorine, ma'am.
Very good, it is chlorine. What we'll be thinking is fluorine because fluorine got highest effective nuclear charge, right? So we'll be expecting as fluorine, but actually it is chlorine. Why? Because effective nuclear charge of fluorine is very much high. So nucleus of this fluorine will attract the all 9 electrons towards nucleus. So this 9 electrons will completely shield the nucleus. Now it is making the it is really makes difficult for the incoming atom to get added. Okay, so because of highest effective nuclear charge, this 9 electrons are attracted towards the nucleus, due to which due to which the incoming electron cannot get added to this fluorine relatively easily. Okay, but it is not the case in fluorine because fluorine got less effective nuclear charge. So this nucleus of chlorine will not attract the 7 electrons as effectively as chlorine. So incoming electron can add relatively easier than fluorine. So if you compare fluorine and chlorine, chlorine can add one more electron very easily than fluorine. Okay, so in periodic table itself, chlorine got highest electron affinity. Okay, so this is not only applicable for 17th group, it is applicable for all the groups. For example, let us take 17th group element: fluorine, chlorine, bromine, iodine, astatine. So since effective nuclear charge is very much high for fluorine, this nucleus will attract the 9 electrons towards itself. So incoming electron cannot add easily, right? So electron affinity is relatively lesser for fluorine, right? So in this case, chlorine got higher electron affinity than chlorine. Chlorine got higher electron affinity than fluorine. In 16th group, what are all the elements present? Oxygen, sulfur, selenium, tellurium, polonium. Oxygen, sulfur, selenium, tellurium, polonium. Among, as we know the trend, right? As we move down the group, electron affinity decreases. So what we'll be expecting, oxygen will have highest electron affinity than sulfur. That is what we'll be expecting. But the actual trend is sulfur will have higher electron affinity than oxygen. The reason is similar reason like fluorine and chlorine, right? So now what we can generalize is, this fluorine, oxygen were second period elements and chlorine, sulfur were third period elements. Okay, so what we can generalize is, always third period elements electron affinity will be greater than second period elements. Okay, that is what the generalization we can do here. Is that clear? Fine, that's it. And last property is acidic and basic properties of few oxides. Basically, metal plus oxygen gives metal oxides, and metal oxides are usually basic in nature. Okay, for example, let us take sodium. If sodium reacts with oxygen, we'll have sodium oxide or sodium peroxide. If sodium oxides or sodium peroxide dissolves in water, it will get converted into sodium hydroxide. What is the nature of sodium hydroxide? Is it acidic or basic?
Basic, ma'am.
Basic. So sodium is a metal and its oxide and its hydroxide is basic in nature. Okay. And similarly for non-metals. Non-metal, if non-metal combines with oxygen to form oxide, then they are acidic in nature. Let us take example of sulfur. Sulfur is a non-metal. What is the oxide of sulfur? It can be sulfur dioxide or sulfur trioxide. If sulfur dioxide or trioxide combines with water, then that will get converted into sulfuric acid. So non-metal oxides are basically acidic in nature and metal oxides are basically basic in nature. Is that clear? Is that
Yes.
clear? Okay. And we have to know what is metal and non-metal also. If an element lose its electron very easily, then that is called electropositive element, and all electropositive elements are metals. Okay. In periodic table, in leftmost corner, elements will have less effective nuclear charge. So elements can lose its electron very easily. So that can gain positive charge. So elements which are present in the leftmost corner of the periodic table are electropositive elements and they are metals. As we move right side in the periodic table, effective nuclear charge is getting increased. So it will attract the electron. So whenever an atom is gaining electron, then they are called electronegative elements, and all electronegative elements are non-metals in nature. Fine. That's it. Another point is, there are few exceptions here. There are few oxides which are neutral. Example, these are some exceptional cases. Okay, carbon monoxide, nitric oxide, nitrous oxide. These were all neutral oxides. Okay, these are all some exceptions. Okay, and there are few metal oxides, they are amphoteric in nature. What is amphoteric in nature? Sometimes they may behave as base, sometimes they may behave as acid. Okay, that is called amphoteric in nature. So metal oxides like oxides of aluminium, beryllium, tin, lead, zinc, copper, these metal oxides may act as amphoteric in nature. Amphoteric oxides. Is that clear? So now we'll move on to few questions, okay? The first question is, which one of the following statement is incorrect in relation to ionization enthalpy? We have to find the wrong statement here. Okay, so the first statement is ionization energy increases for successive electrons. Is that right?
Yes, ma'am.
Yes, it is right. We have to find the wrong statement here. Second option is the greatest increase in ionization enthalpy is experienced on removing one electron from core noble gas configuration. Is that right?
Yes, ma'am.
Yes, because noble gas configuration is very stable configuration and we cannot remove electron from that. So we have to supply more amount of energy. So second statement is also right. End of valence electron is marked by a big jump in ionization enthalpy. Is that right? End of valence electron is marked by a big jump in ionization enthalpy.
Yes, ma'am.
Definitely that is right. Fourth option is removal of electron from orbital bearing lower n values easier than orbital with higher n value. Is that right?
No, ma'am.
No. Lower n value means the electron is present nearer to the nucleus. So removing the electron which is present nearer to the nucleus is very difficult. So we have to supply more amount of energy. So for which ionization energy will be more. But here they are telling like we have to supply. Removing the electron is very easy. The electron is present in the shell which is nearer to the nucleus, which is wrong. Second question. Okay, what is the question? Considering the elements boron, aluminium, magnesium, and potassium, the correct order of their metallic character. What is metal? Capacity of an atom to lose its electron, right? That is considered to be metal. So we have to arrange boron, aluminium, magnesium, and potassium based on their metallic behavior. So to arrange these elements, we have to know the positions of all these four elements. Okay. So boron, aluminium were in 13th group. So boron, aluminium, this is in 13th group. So magnesium in second group and potassium is in first group. So what are the first group elements? Lithium, sodium, potassium, rubidium, cesium. And second group elements are beryllium, magnesium, calcium, strontium, barium, radium. Okay, here we have to consider boron and aluminium, magnesium, potassium. So what is metallic character? Capacity of an element to lose its electron. So to lose an electron, atom should have less effective nuclear charge. So as we move from left to right in a periodic table, effective nuclear charge increases. So elements which are present in the leftmost corner of the periodic table will have less effective nuclear charge. So according to that, which element will have less effective nuclear charge among these four elements?
Potassium.
Potassium, right. So potassium will lose its electron very easily. So potassium will have highest metallic property. So potassium is the highest one. So all the options were ruled out. Definitely option 4. After potassium, it is magnesium, right? And after magnesium, we have to compare between boron and aluminium. Both the elements were in 13th group, but as we move down the group, effective nuclear charge decreases, so capacity of losing electron will get increased. So aluminium will lose its electron easily, so aluminium will have more metallic behavior than boron. So answer is option 4. Next question. This is just opposite question. Considering the elements boron, carbon, nitrogen, fluorine, and silicon, the correct order of their non-metallic character is. I think you can try this question. You have to check for the non-metallic character.
Option C, ma'am.
Okay. Option C. Okay. Fine. It is option C. Because which is considered to be non-metal, the elements which are present at the rightmost corner, right? So among these elements, fluorine is present in the rightmost corner. So based on the position itself, we can tell the proper order, right? Shall we move on to next question?
Yes, ma'am.
Okay. Okay. The species argon, potassium plus, calcium 2 plus contain the same number of electrons. In which order do their radii increases? See here, potassium, argon, calcium. All the three species got same electrons, which means these three elements are isoelectronic species. And we have to arrange the arrange these species based on their radius. So have to arrange that.
Option C, ma'am.
Okay, option C. Varshini's answer is option C, right? We'll check Kana. Actually, as far as argon is concerned, number of proton is 18, number of electron is also 18. As far as potassium is concerned, atomic number is 19, but here this is potassium plus, we have to remove one electron, so electron count will be 18. Calcium, the atomic number is 20. Since it is in 2 plus oxidation state, the electron count is just 18. Right? All the elements seems to have same number of electron, but definitely size will vary. How it will vary? Here, there are 18 protons. This 18 proton is holding 18 electrons. That is fine. Here, 19 proton is holding 18 electrons. So 18 electrons will experience more effective nuclear charge, right? So here, size of the potassium plus will be lesser than argon. Is that right? Is it right? Because here we have 19 protons and just 18 electrons, right? So this 18 electrons will get attracted towards nucleus more than the argon. And in calcium 2 plus there are 20 protons and there are just 18 electrons. This 18 electrons will experience more attraction towards the nucleus. So size of argon will be greater than potassium plus, and size of potassium plus will be greater than calcium 2 plus. So whenever you are talking about the radius of isoelectronic species, please remember this order. Always anion's size will be greater than atom. Atom's size will be always greater than cation. As far as cations are concerned, if the positive charge is getting increased, size of the species will get decreased. And as far as anions are concerned, if negative charge is getting increased, size of the anion will get increased. Okay, that's it. So here the order is option 4. Now we'll move on to next question. Among the oxides of aluminium, silicon, phosphorus, and sulfur, the correct order of acid strength is dash. Generally, oxides of non-metal will have acidic character. So based on that logic, you have to arrange these oxides. So for which you have to know the positions of aluminium, silicon, phosphorus and sulfur. So in 13th group, we'll be having boron, aluminium. In 14th group, we'll be having carbon, silicon. In 15th group, we'll be having nitrogen, phosphorus. And 16th group, oxygen, sulfur. So they are talking about aluminium, silicon, phosphorus and sulfur. Among these four elements, which element will have more non-metallic behavior?
Sulfur, ma'am.
Sulfur. So sulfur's non-metallic behavior will be greater than rest of the elements. So oxide of sulfur will be more acidic, right? So definitely answer is option 4. So after sulfur it is phosphorus, after phosphorus it is silicon, and after silicon it is aluminium. So aluminium is in the leftmost corner relatively, so whose effective nuclear charge is a little lesser. So metallic property may be a little higher than the rest of the elements. So answer is option 4. Next question. Ionic compounds are formed most easily with? What is ionic compound? Compound with ionic bond. What is ionic bond? A chemical bond formed by complete transfer of electron, right? So let us take A and B. To form a ionic bond between A and B, A has to lose its electron completely. So that electron has to be transferred to B. So A will gain a positive charge and B will gain a negative charge. And the electrostatic force of attraction between A plus and B minus is basically the ionic bond, right? So to form this ionic bond, A should have the capacity of losing electron and B should have the capacity of gaining electron. So based on this logic, please find the option.
Option A, ma'am.
Okay. A should lose its electron easily, right? So for that, which means ionization energy has to be higher or lower?
Lower.
It should be lower, right? So this element should have low ionization energy, right? And similarly, B minus means this element should have the capacity of gaining electron. So electron affinity should be higher or lower?
Higher.
Higher. Higher electron affinity. So what is the answer? High electron affinity and low ionization energy. Answer is option
C.
No. Low ionization energy and high electron affinity. It is not C. Low ionization energy, high electron affinity. So answer is option 2. Is that clear?
Yes, ma'am.
Okay, Kana. Now we'll move on to next question. Okay, arrange the following elements in increasing order of electronegativity, which is very simple. So we know the position and also we know the trend.
Option 2, ma'am.
Okay, let us see the positions. Okay, carbon, nitrogen, oxygen, fluorine, and silicon is here. As we move from left to right in the periodic table, electronegativity increases. So fluorine got highest electronegativity. So for first option and second option were ruled out. And after fluorine, which got highest electron affinity?
Oxygen.
It is oxygen. Okay, it is oxygen. After oxygen, it is nitrogen. Okay, after nitrogen, it is carbon, then silicon. Okay, is that clear?
Yes, ma'am.
Okay. Next question. Amongst, actually, this is a neat question, okay? And this is also a neat question. I think this is a very recent question. This is from Neet 2024. Among group 16 elements, which one does not show minus to oxidation state? So, which is group 16 elements? Oxygen, sulfur, selenium, tellurium, polonium. This is 16th group element, and they're asking us to find the element which will not form or which will not show minus to oxidation state. To show minus to oxidation state, that element has to gain 2 electrons, right? So to gain 2 electrons, that element should have high effective nuclear charge, right? But as we move down the group, effective nuclear charge will get decreased, right? So based on this concept, tell me the answer. Which will not gain 2 electron then? As we move down the group, effective nuclear charge decreases. So the element with lowest effective nuclear charge cannot gain electron. So that element cannot show minus to oxidation state. Then which will be the answer?
Option 2, ma'am.
That's it. Polonium is present at the lowest. Polonium is the lowest element, right? Which will have lowest effective nuclear charge, so that cannot gain 2 electron. Next, this question. Arrange the following elements in increasing order of first ionization enthalpy. Very simple, but you have to apply all those factors here. Lithium, beryllium, boron, carbon, nitrogen. So what we'll be expecting as we move from left to right in a periodic table, effective nuclear charge increases. So ionization energy also increases. That is what we'll be expecting. Okay. But ionization energy not only depends on effective nuclear charge, but also other factors like a half filled and completely filled configuration, penetration effect, and all that, right? So to understand that, please write the electronic configuration of all the elements. So atomic number of lithium is 3, the electronic configuration is 1s2, 2s1. Atomic number of beryllium is 4, the electronic configuration is 1s2, 2s2. And atomic number of boron is 5, the electronic configuration is 1s2, 2s2, and 2p1. This is 1s2, 2s2, 2p2. And this is 1s2, 2s2, 2p3. So lithium is at the leftmost corner. Effective nuclear charge is very less. Definitely lithium's ionization energy will be very much less. So lithium will be at the lowest corner, right? Among beryllium and boron, as we move from left to right, effective nuclear charge increases. But the problem here is the electron what I'm going to remove is present in S subshell. The electron which I'm going to remove from boron is present in P subshell, which is easy. Which is easy?
The one in P section, ma'am.
That's it. So boron's ionization energy will be lesser than beryllium, right? So boron, then beryllium. Okay. And now we'll compare carbon nitrogen. Definitely nitrogen's ionization energy will be greater than rest of the elements because it is half-filled configuration. So carbon and highest is nitrogen. So which option is right? Fourth option. That's it. This is also a neat question. This is another neat question. The element expected to form largest ion to achieve the nearest noble gas configuration is. The element expected to form largest ion to achieve the nearest noble gas configuration is. So sodium, to attain noble gas configuration, sodium has to lose its electron. So the ion will be Na plus. How about fluorine? To attain the noble gas configuration, fluorine has to gain one electron. So F minus one, F minus one is the ion. How about oxygen? To attain noble gas configuration, whether oxygen has to lose electron or gain electron.
It has to gain electrons,
Has
ma'am.
to gain electron. Have to gain 2 electrons actually. Right. How about nitrogen?
3 electrons should
3
gain.
electrons. Now, among these ions, which is the largest one? All these were isoelectronic species now. So, among isoelectronic species, how we have to choose the size? I've told you the order already.
Nitrogen, ma'am.
Very good. Because anion's size will be always greater than atom. Atom size will be greater than cation. As far as anions are concerned, anion with more negative charge will have biggest size. That's it. Now the answer is option 4. Now it is very easy. This is also a neat question. You have to write the IUPAC nomenclature of the element whose atomic number is 119.
Option B, ma'am.
Second option. That's it. Very good. Next question. From the following pairs of ions, which is not an isoelectronic pair? We are provided with one pair in all the options, and we have to find pair which is not an isoelectronic one. This is also a neat question.
Option C, ma'am.
Very good, Anu. It is option C. Because as far as Fe2 plus is concerned, the electronic configuration will be argon. Originally, configuration is 4s2 3d6. If we are removing 2 electron, the configuration will become 4s0 and 3d6. Here it is manganese 2 plus. The original configuration is argon 4s2 3d5. Now we are removing 2 electrons, then the configuration is argon 4s0 3d5. So here it was 26 electron and we are removing only 2 electron. So it is 24. Here it is 25 and we are removing 2 electrons. It is 23. So it is not isoelectronic species. So answer is option C. Next question. Very easy. Again, this is a neat question. For the second period elements, the correct ionization order of first ionization enthalpy. Very easy. Cakewalk.
Ma'am, option B.
Very good. Option B. This order we already know, right? And among oxygen and sulfur, oxygen and nitrogen got half-filled configuration. So nitrogen will have higher ionization energy than oxygen. So second one is the right answer. Is that clear? Shall we move on to next question?
Yes, ma'am.
Okay. Which of the following oxide is most acidic in nature? So again, check for the position of magnesium, barium, beryllium, and calcium. And among all those elements, check which element cannot lose its electron. Then from which we can identify which is more acidic.
Ma'am, option 2, ma'am.
Very good, Anu. It is option 2. Because beryllium, magnesium, calcium were second group elements. So second group elements are beryllium, magnesium, calcium, strontium, barium, and they are talking about beryllium, magnesium, calcium, and barium. So as we move down the group, effective nuclear charge decreases, so capacity of losing electron will get more. So barium can lose its electron easily, so this will behave, or this barium will have more metallic nature. So metal oxides will be basic in nature, but they're asking for acidic in nature. So definitely it is beryllium oxide. So answer is option 2. And this question, the correct order of atomic radii in group 13 elements. So what are all the elements present in group 13? Boron, aluminium, gallium, indium, thallium. what we'll be expecting is, as we move down the group, size of the atom increases. So the expected order is boron, aluminium, gallium, indium, thallium, but that is not the case here, because the electronic configuration of boron is atomic number is 5. The electronic configuration is 1s2, 2s2, 2p1. And as far as aluminium is concerned, the electronic configuration is neon, 3s2, 3p1. And for gallium, the electronic configuration is argon. The outermost configuration is 4s2 and 4p1. But the gallium's configuration will have d electrons also. Okay, so this will have 3d10. Usually, as we move down the group, effective nuclear charge decreases, size of the atom should be more, right? But as far as gallium is concerned, here we have inner electrons as d electrons. Actually, inner electrons are supposed to shield the nucleus, but here the inner electrons are d electrons. Usually, if the inner electrons are s electron, this s electrons will shield the nucleus very perfectly, but p electron will not shield to that extent. D electron will not shield to that extent, and f electrons will shield the nucleus very poorly. Here the inner electrons are d electrons. This d electrons cannot shield the nucleus as perfectly as s electrons and p electrons do. So here gallium's nucleus relatively will get exposed, and this nucleus will attract the fourth shell towards itself. So the radius of gallium will be little lesser than aluminium. Okay, this is called transition contraction. You would have studied about lanthanide contraction, or you will be studying in future about lanthanide contraction, D and F block element. Here, this is called transition contraction. Okay, so boron, aluminium, gallium, among these three, gallium's size will be lesser than aluminium. So, what will be the answer then? So, what will be the answer? Option 4. Okay, the expected order is this, but this is wrong. Okay, a gallium size will be lesser than aluminium. And next class, I'll help you to write the electronic configuration of all the group elements without knowing without knowing its atomic number itself. See, we don't want to know the atomic number of gallium, indium, thallium, and all. Without knowing the atomic number itself, just from the position, we can write the electronic configuration. In next class, I'll teach you that. Okay. Let us see one question. Match the following. In column 1, they have given you few oxides, and column 2, they have given the nature, basic acidic nature and all, and we have to match those. And I've given you few exceptions also. Use that and please match the following. This is also a neat question.
Ma'am, option A.
Okay, here sodium is a good metal. So oxide of metal will be basic in nature, right? So first one is B. So option 2 and 3 can be ruled out, right? And how about chlorine? Chlorine is present at the rightmost corner of the periodic table. So it is pure non-metal. Non-metal oxides will be acidic in nature. So fourth one will be 3, but we cannot screen among 1 and 4. Again, nitrous oxide. Nitrous oxide is a neutral one. It is a neutral one, right? Carbon monoxide, nitric oxide, nitrous oxide. These three oxides are neutral. So third one we have to connect it to A, right? So what is the answer then?
Option 4, ma'am.
Yes, metal oxides, oxides of aluminium will be amphoteric in nature. So answer is option 4. Shall we work out one last question, or we'll wind up the session? You want me to wind up the session, or we'll see one question? Okay. Okay, one more question. Okay, last question. Definitely, this is last the question. Or let us take this as an activity. Please take this question as activity. Here, they have given you the element whose atomic number is 114, and they're asking us to locate this element, whether this element is present in carbon family, oxygen family, nitrogen family, or halogen family. Okay, so for that you have to know the electronic configuration. So as I've promised you, next class I'll teach you how to write the electronic configuration of elements without knowing the atomic number itself. Okay, so by understanding that, you can answer this question. Okay, okay, Tatvatika, your answer is right. What will be your justification then? You have written the electronic configuration itself based on Huff's principle or what?
No, ma'am, I was just done like boron, carbon, nitrogen, oxygen, fluorine, and reversed from 118.
Okay, fine, fine. That was really a good idea. Okay, fine. So now shall we wind up the session? So actual answer is carbon family, but next class I'll give you the proper justification. Okay, and I'll teach you how to write the electronic configuration without knowing the atomic number. Okay. Is there any other doubt, Varshini, Anushri?
No, ma'am, no doubt for me.
Okay, Kana. Okay, fine. Then shall we wind up the session, Tatvatika?
Yes, ma'am. Thank you, ma'am.
Okay, bye guys. Bye bye. Good night.
Good, good night, ma'am. Thank you, ma'am.